Now, I want us to look at another application of diode as a semiconductor device, which is a diode clamper circuit, which is a diode clamper circuit, which is a diode clamper circuit. Now, with the diode clamper circuit, I will have an energizer, which is my AC energizer. Then I'll say with this energizer, for example, it is 10 volts P, 10 volts P. Now, in series with this energizer, I will go and connect a capacitor. Now, the capacitor that I'm going to connect, it is an electrolytic capacitor or a polarized capacitor, which means it's a capacitor with polarity. It has got a negative side and it has got a positive side. Then I will say this capacitor, I'm connecting in this manner. The positive side is connected there and the negative side is connected there. Positive and negative. Or I will indicate which side is the positive side and which side is the negative side. Then continuation. Then I will have a diode. Now, how I have connected the diode, it is very important with respect to how I have connected my capacitor, which means I must make sure that I align the two connections. I must make sure that I align the two connections so that it can give me the correct result or the correct output. Then how you have connected your capacitor, that is how you need to connect your diode. Then I connect the positive side of the diode there, and I connect the negative side of the diode here. Then I have my output resistor there. I have my output resistor there. Then I will say this is 10 kilo ohm resistor, which is my load resistor. That is where I will measure my output. My diode T1, I say that is 0.7, sorry, not 0.7. My silicon diode, that is my silicon diode. Then I say this is 210 microfarad capacitor. That is my 210 microfarad capacitor. Now, your diode and the load resistor, they must be connected parallel to each other. The diode and the load resistor must be connected parallel to each other. Now, you will see that this circuit is similar to the clipper circuit. This circuit is similar to the clipper circuit. The difference is the clamper circuit has got a capacitor connected in series with the source. The clipper circuit has got a resistor connected in series with the source. That is the difference between the two. One has got a capacitor connected in series, one has got a resistor connected in series. Now, then I will go and say, now let's look at how the current is going to flow. Let's look at how the current is going to flow. Now, positive, negative there. Then I represent this with a graphical sketch. I represent this with a graphical sketch. All the way positively, negatively there. Ten peak minus 10 peak. Now, if you look at this signal here, you will see that with this type of a circuit, we want to see how is the response of the output with respect to the input. How is the response of the output with respect to the input? Now you will see that we need this component that will tell us the response. It's either of a forward bias or of a reverse bias. It's either forward bias or reverse bias. But now, if I look at this very carefully, now I will go and say, I need to switch on this component here. I need to switch on that component there. And for me to switch on this component, which means I must reach a voltage of 0.7 volts. I must reach a voltage of 0.7 volts. Now, if I look at how the current is flowing, which is a what? Which is a conventional current, energized from the source through the conducting wire. Then it met this component there, which is an electrolytic capacitor. And we know that with the capacitor, you've got two metal plates which are connected parallel to each other. But now, there must be magnetic flux that builds around these two plates so that you can have an induced EMF. Now, with that induced EMF, which means now it's going to allow current to flow. But now, with this induced EMF, or with this magnetic flux which is building around this component, it must be based on how is it connected with respect to your source. Now, with this type of component, we know that that is going to happen, or that is going to occur when charges are being stored. When charges are being stored. Now, with the charges being stored, which means I must connect this component correctly. Now, with the continuation, or with how current is flowing, then we'll see that this component will be able to store charge. Now, with this component storing charge, which means magnetic flux are building around this component. Now, when magnetic fields are building around this component, which means the induced EMF is gonna occur, which means I will have a VC, or a voltage across that component there. I will have a voltage across that component. Now, once I have a voltage across that component, which means I'm going to allow current to flow. And when the current flows, it gets to that direction, and also it gets to that direction there. It's splitted there, which means these two being splitted, coming to recombine, this one and that one, they are parallel to each other. The magnitude of this and the magnitude of that, the magnitude of this and the magnitude of that, now it must allow this component to be at forward bias mode. Now, if this component, it is at forward bias mode, which means now it's allowing the current to flow, which means the characteristics of the output, needs to happen within the three conditions. The characteristics of the output needs to happen within the three conditions. You must have one, what we call your V output peak. We must have a V output peak. Now, with the V output peak, it's either it is of a maximum or it is of a minimum. Your V output is either it is of a maximum or it is of a minimum. And then with this maximum and minimum, it must be a maximum or a minimum of turning point. It must be a maximum or a minimum of a turning point. Now, with this turning point, it's either it is of a positive turning point or a negative turning point. It's either it is turning positively or it is turning negatively. It's either it's turning positively or negatively. But now with this turning point, positively, that is your maximum turning point. Negatively, that is your minimum turning point. Now, that is the first two conditions. So that is the first condition that needs to happen. That is your first condition that needs to happen. Now, if I look at these, with the circuit, or sorry, with the current flowing, if this component, it is at forward bias, then this component, it is storing charges. If this component, it is at forward bias, that component, it is storing charges. Then I will go and say, I need to measure my V out. Then I will say, the first V out that I need to measure, is going to be a V out whereby this component has been switched off. So which means the first thing that you need to do, or what you need to put into consideration, it is first switch on that component there. first switch on that component there. When you switch on that component, you charge that component there. I want you to be very careful and I want you to listen very carefully. You switch on this component, you charge that component there. That is the first condition that you do within this circuit. You switch on this, you charge there. Now, when this one is switched on, which means it's forward bias, then 0.7 volts has been established. But it is during when? During the positive cycle. It is happening during the positive cycle. Then I will go and say, once this is switched on, what is the voltage that I'm going to measure there? What is the voltage that I'm going to measure there? I am going to measure 0.7 volt, which means during forward bias, I have measured 0.7 volt. During forward bias, I have measured 0.7 volt. Now, it's a positive or a negative 0.7 volt. Looking at how I have biased this component, I biased it during the positive cycle, which means that voltage, it is what? It is a positive 0.7 volt. Once I determine D, then I go and ask myself, which means that is your output peak voltage. That is your output peak voltage. Is it maximum or minimum? How do I determine this maximum and minimum? It's maximum or minimum based on turning point. Is it turning positively or turning negatively? If it's positive, it's maximum. Negative, it's minimum. In this case, it is positive. V out peak turning positively, which means that is your maximum peak. Graphically, I need to turn with respect to the output at 0.7 volts positively. Now, if that is how the graph is, if that is how the output is, then I know that the output according to this circuit, it must be an exact replica of the input. It must be an exact replica of the input. But now with this circuit, then I will go and say, my output, it is going to be an output whereby, let me just do this. It is going to be an output whereby, now I will go and say, I need to turn 0.7. Where is 0.7? If that is 0, which means more or less 0.7 can be there, 0.7 volts. I need to have a turning point at 0.7, which means my graph needs to turn at 0.7 volt. My graph needs to turn at 0.7 volt. Now, if my graph is turning at 0.7 volt, it needs to have a point of reference, which means this 0 is no longer my point of reference. I have shifted my graph from its original point of reference into a new point of reference. I have shifted my graph from a point of reference or original point of reference to a new point of reference. Now, I need to go and determine what is that new point of reference. What is that new point of reference? Now, I'll just draw the complete of this and I will explain it to you. Don't mind the size. Don't mind the size. This is just for the purpose of explanation. But it must be the replica. It must be the replica of the input. It must be the replica of the input. Don't mind the size. Now, then it says my graph turned at 0.7 volts. If your graph turned at 0.7 volts positively, you will see that that is the maximum. Now, if this is 10, and 0.7 volts is somewhere there, and I need that peak of 10, from 10 to 0.7, which means I must take this graph, shift it downwards up until I reach 0.7 volt, or up until I align this peak to 0.7 volt. That is what I have done there. Now you will see that this type of circuit, with how the graph is, or with how the replica of the input is being shifted downwards, being shifted downwards, that is your negative Clampter circuit. That is your negative Clampter circuit. Then I will go and say, since I can see that, oh, that is only the portion of the maximum, which means the graph will shift downward. Most of your graph, it's no longer half of positive, half of negative, but it is more or less about 90% negative, 10% positive, which means it has shifted downward. Because it has shifted downward, it becomes your negative Clampter circuit. But what are the magnitude? The first magnitude that I determined, it is the magnitude of the turning point, which is your maximum turning point. Then I will go and say, once I determine the magnitude of the turning point, which is maximum, then I can go and say, what is my VC? Of which in this type of circuit, your VC, in this type of circuit, your VC, that is the second thing that you must consider. Your VC becomes your Vref. And it's either a positive reference or a negative reference. Your VC is your reference voltage. It's either a positive or a negative reference. But now, when this signal started, your Vref was 0, which means the voltage here was also 0, the voltage here was also 0. But now, during the gradual increment of your magnitude to your input voltage, when you switch on this, and also that one was charging, which means your signal shifted. And when your signal shifted, it shifted to a point whereby its maximum is no longer 10, but the maximum becomes 0.7 volt. But now, if the maximum becomes 0.7 volt, which means your point of reference also changed. But the point of reference now is going to be determined by how much is the voltage determined, or how much is the voltage established within that component there. Then your Vref, in this case, your Vref, in this case, it becomes your V out. Sorry, not your V out. Your VC is equals to, according to Kirchhoff, it says the voltage that you measure here and the voltage that you measure here, adding the two must give you the supply voltage. The voltage here plus the voltage here must give you the supply voltage. Then you will see that your V out, it is going to be your V out of V in minus, so your VC minus your V out. Your VC minus your V out. In this case, your V out is what? Your V out is 0.7 volt, which means here it is going to be 9 minus 0.7, which is what? Which is your 8.3, 10, sorry. Am I getting 9? Which is your 9.3 volt, which is your 9.3 volts. Now, once you establish this 9.3 volts, you will see that this is a positive 9.3 volts. Yes, it needs to be a positive 9.3 volts. Why? It's because when I charge this component, how did I charge that component? I charge that component during the positive cycle. I charge this component during the positive cycle. Now, because I charge during the positive cycle, it must be a positive 9.3. But when I measure here, due to this as a maximum turning point, you will see that graphically, these in terms of the measuring voltage, these in terms of the measuring as a V reference, this one is minus 9.3 volt. Because with these, that has shifted your signal downwards. that has shifted your signal downward, of which your output as a reference in terms of the VC, it led your signal to have a reference at a minus position there, which means your reference needs to be 9,3 volts there. When I charge it, it is positive, but the signal shifted as a reference to what? Minus 9,3 volt. That's why I say your VC, it is your reference voltage. It's either positive or negative, which means in this condition, it is at a negative magnitude graphically, which means it has shifted downwards here. Now, once you get these, then you're going to say, what is the last step? The last step, it is what? It is how it is telling your V out peak. But now your V out peak, well, you will see that now you are doing positive, 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 positive. You are charging this, switching on that one day. Then you get to a point of zero. Now the cycle change. When the cycle change, which means now you are looking at the negative cycle. You are looking at the negative cycle. You have done the maximum turning point. You have done the point of reference with respect to VC, but now I need the minimum turning point. And the minimum turning point will exist when your signal is at a minimum cycle, so which is at a negative cycle, which means now you will have got negative, positive. Your cycle has changed. When your cycle changes, which means now your current is going in that direction. And when the current is going in that direction, you will see that it will force this component to go into reverse bias. It will force this component to go into reverse bias. And when this component goes into reverse bias, when this component goes into reverse bias, which means it's an open switch, current will flow continuously. It's not going to flow with respect to this component, but it's going to flow continuously there. When it flows continuously there, then now this component no longer have a voltage drop dependent on that one there. It must have its own dependent voltage. This voltage plus that voltage must give you a supply voltage. This voltage plus that voltage must give you a supply voltage. But now, with respect to these, then I will go and say, what will be my V out? What will be my V out? Now, during which cycle is your V out? During which cycle is your V out? Remember, your V out must be given by your V in. Your V out must be given by your V in minus VC. Your V out must be given by V in minus VC. Now, within this point, your V out must be given by V in minus VC. Within this point, what is your V in? You will see that your V in is 10. You will see that your V in is 10. When your V in is 10, positively 10, negatively 10. Positively 10, negatively 10. Negatively 10 because now your signal has changed direction, which means here you will have minus 10 minus the VC that you charged with. It's what? Positive 9,3, which means it's minus 9,3. That leaves this one to be minus 19,3 volt, which means here you've got minus 19,3 volt. That is a negative Clampter circuit. That is a negative Clampter circuit. Now, how is the time frame there, Andy?
You can go a few minutes, or we can cut it here, take a screenshot and move on.
Screenshot, cut it here, then we'll re-record again. If it's a few minutes, because I will take the same exact minutes to explain the other one.
Okay.